All right, so starting at about section 1.4 of the statistics material, we're going to start to encounter formulas, and we're also going to start to encounter criteria for deciding if certain values in a data set are unusual and things like this. So let's take some time and review a little bit about how to evaluate formulas and how to compare numbers to one another. Okay, so for evaluating formulas, we're just going to take numbers and plug them in for the variables in the formula, and then we're going to use the correct order of operations to simplify them. The correct order of operations is parentheses, exponents, multiplication and division go in the same step, and then addition and subtraction go in the same step. So we sometimes call this PEMDAS, or I learned it, please excuse my dear Aunt Sally. But now that said, you're allowed to use a calculator in this class, and in fact I'm inviting you to please use the Desmos calculator, which is the calculator that I have open right here, okay? And if you use the Desmos calculator, if you just type the expression into the calculator exactly the way it looks on the page, you can be sure that Desmos will do it correctly. It'll do it in the correct order of operations. Now, this is not the case for other kinds of calculators, a basic calculator. A lot of times the calculator on your phone won't do the order of operations correctly unless you force it to. So it's important to use a good calculator. Or if you're not going to use a good calculator and you just want to use a basic calculator, that's fine, but then it's on you to review the correct order of operations and learn how to use your calculator so that it'll do the correct order of operations. I'm just going to show you how to do this on the Desmos calculator, which once again, you're welcome to use throughout the duration of this course. So, example 1 says, suppose that z equals a minus b all over c. We're asked to calculate z if a equals 5, b equals 3.2, and c equals 0.7. So to do that, we would just plug those numbers in. We would say z equals a, they said to replace with 5, okay, b they said to replace with 3.2, and c they said to replace with 0.7. So now in my calculator, the first thing that I want to do is hit the fraction bar, and I can do that by hitting this button here, or I could do it by hitting the division sign, or I could type the division sign on my keyboard. And in any case, this little fraction symbol will open up, and I can type in 5 minus 3.2, and then to get down to the denominator, I can use the down arrow, and then say 0.7, and hit enter, and there we go. Let's round this to 2 decimal places, so we'll call this approximately 2.57. Okay, number 2 says, suppose that UF equals Q3 plus 1.5 times IQR. Calculate UF if Q3 equals 17 and IQR equals 5. Something that might trip you up here is that you might think that U and F are 2 different variables, but apparently they just stand for one quantity. And you might be confused and think Q3 means something like Q cubed, like we need to put a number in for Q and then raise it to the 3rd power or something. But that's also not the case. Q3 we're told is just the number 17, so we're going to replace the entire symbol Q3 with a 17. Right? So UF would equal Q3, right, which is 17, plus 1.5 times IQR, which is 5. Okay? And that's what that would look like. Now, these parentheses indicate multiplication. Okay? If there's not an operation written, if there's not like a plus or a minus or a divide or something, then it's assumed that it means multiplication. Once again, we're going to type this into our Desmos calculator the way that it looks. 17 plus 1.5 times 5, and that's 24.5. And that's exactly equal to 24.5. I didn't do any rounding, so I can use an equal sign there. Now, one common mistake that students will make when they're typing this into their calculator is they'll do something like 17 plus 1.5, and then they'll hit enter, and then they'll say that answer, 18.5 times 5, and they'll end up at the wrong place, right? So don't do that. The order of operations says that you want to do the multiplication first. So if you want to do this one step at a time, you would actually start with the multiplication, right? 1.5 times 5, and then you would add that to 17. You would say 17 plus your answer, 7.5. And then you can see that you end up with 24.5, just like you should. The much safer thing to do, of course, is to just type it in exactly the way it looks into the Desmos calculator, and Desmos will do the rest for you. So that's all I have to say about evaluating formulas for now. One of the things that we want to do with these formulas is we want to be able to say, okay, if I get a certain number, like if I calculate a value and it's more than 7, then I'm going to consider it to be an unusual value, right? Something like that. And so in order to make those kinds of comparisons, it's useful for us to think about the number line a little bit as we're comparing numbers. So on the number line, the way the number line works is it's an imaginary line that we use to conceptualize the real numbers. The farther to the left a number is on the number line, the smaller it is, and the farther to the right a number on the number line is, the larger it is. We usually imagine 0 to be right in the center of the number line. Anything to the left of 0 would be a negative number, so this would be -1, -2, -3, right, and so forth. And anything to the right of 0 would be a positive number, so this would be 1, 2, 3, 4, and so forth. Let's practice graphing these numbers on the number line. So a -2 would mean starting at 0, I'm going to go 2 spaces to the left, and that would be -2 right there. Okay. A +3, I would go up 1, 2, and 3, and there's a +3. 1.5 is going to fall somewhere between 1 and 2, right? It's going to be 1.5, right? 1.5 is right there. -0.25. You may recall that -0.25, or that 0.25 is just the same as 1/4, right? So if it's a -0.25, then it's going to be a -1/4. So if I split the space between 0 and -1 into 4 parts, then each of these spaces is 1/4, right? So -1/4 would be right there. So this is -0.25. -7/4. Well, this is -1/4, -2/4, -3/4, and -4/4 is the same as -1. But I need to get all the way to -7/4. So I need this. If this is -4/4, then I've got -5, 6, 7. -7/4 is right there. And then finally 5/2. Well, let's see. The space between 0 and 1, if I mark the space right in the middle, that's 1/2. So I have 1/2, 2/2, 3/2, 4/2, and then 5/2 would be right there. Okay. You'll have an opportunity, I think, to practice with this in some homework, right? To get used to putting things on the number line. But the moral of the story is, if you can think in terms of the number line, then any number that's to the left of another number is the smaller number, right? The number that's on the left is the smaller number. So we'll try to have this picture in mind, even if we don't draw it out. We'll try to have a picture in mind, and we'll think, okay, any number to the left is the smaller number. Now, the symbols that we use to indicate which numbers are bigger and smaller sometimes cause students confusion as well. We're familiar with the equal sign already. If two numbers are equal, that means they have exactly the same value, or in other words, they fall on the same place on the number line. But if we have a statement that says this, we would read this: A is less than B, and that means that A is to the left of B on the number line. We could rephrase that as B is greater than A, because of course if A is less than B, then it must be the case that B is greater than A. So we can read this symbol from left to right: A is less than B, or we can read it from right to left: B is greater than A. In either case, note that this symbol means exactly what it looks like. The smaller part of the symbol, the point, right, is pointing toward the smaller number, and the larger part of the symbol is opening up towards the larger number. Now, if the relationship were reversed, okay, if A was larger than B, then we would have this situation: A would be to the right of B on the number line, or in other words, B would be to the left of A on the number line. And we would write this symbol. We would say A is greater than B, right? So we can read that left to right: A is greater than B, or we could read it right to left: B is less than A. But again, note that the symbol means exactly what it looks like. The smaller part of the symbol is pointing toward the smaller number, in this case B, right? It's pointing toward the smaller number. Let's just practice. So we'll fill in the blank with the appropriate symbol, either an equal sign if the numbers are the same, or a less than sign or a greater than sign, depending on the relationship between the numbers. So if we're comparing 2 and 5, again, you can think of the number line, but 2 would be to the left of 5, so 2 is smaller than 5. So I'm going to draw the smaller part of the symbol pointing towards the 2, and I would say 2 is less than 5. If we were comparing -2 and 5, again, -2 would be to the left of 5 on the number line, so -2 is less than -5. If you need to pause the video and kind of think about these before you fill in the blanks, that's totally fine. Do what you need to do in order to make sure that you're grasping the concept. If I wanted to compare 2 and -5, now this one may seem a little bit tricky because 2 is smaller than 5, but notice that the 5 here is negative. So the -5 would be to the left of 0, and the 2 would be to the right of 0, which means 2 is to the right of -5. 2 is bigger. 2 is bigger than -5, right? If they were both negative, then both of these numbers are going to be to the left of 0, but -5 is going to be even further away from 0 than -2 is. So -5 would be smaller than -2. Or in other words, -2 would be greater than -5. Okay, if you're dealing with fractions, don't be scared. Fractions are just numbers. 2 apples is less than 4 apples, so 2/5 would be less than 4/5. Now, 3 halves, that's 2 halves, which is 1, plus another half, so that's the same as 1 1/2. Well, that's exactly what 1.5 is. These numbers are equal. They're the same number. And we've talked previously about the fact that with decimal numbers you can add or remove zeros to the end of a decimal number, and it doesn't change the value of the number, so these numbers would also be equal to each other. Okay, so this is how comparisons of numbers works. Now, if you're comparing 2 decimal numbers, it may be helpful to add or remove zeros from one or both numbers so that they have the same number of digits, and then that will make the number easier to compare. Let me give you some examples. If I'm comparing 0.2 and 0.5, these both have been rounded to 1 decimal place, and so I can compare them easily. I know that 2 is less than 5, and therefore 0.2 is less than 0.5. But if I'm comparing 0.2 and 0.05, now this is a little trickier because 0.2 only has 1 digit and 0.05 has 2 digits. So what I need to do is add a 0 to the end of this one so that these two things are the same, right? So if I add a 0 to the end, then I notice that what I'm really comparing here is 20 and 05, right? In other words, 20 and 5. 20 is bigger than 5, so 0.2 would be bigger than 0.05. For part C, these numbers are going to be equal. Again, you can just add a 0 to the end of that first number, and you can see that, okay, yeah, they're the same number. But for part D, 0.2 is greater than 0.02. And again, that's because what I'm really comparing is a 20 and a 2. Okay, I'll let you pause the video and see if you can do the last 4 there at the bottom. Okay, here are my answers. 0.574 is less than 0.575. 0.9 is greater than 0.84. 0.754 is less than 0.87. But 0.754 is greater than 0.67. Okay, so this is how comparing decimal numbers worked. Now, these inequalities that we've talked about so far, the greater than and the less than symbols, are called strict inequalities. You're also probably familiar with what are called inclusive inequalities. That would be these ones, right? This one means less than or equal to, and this one means greater than or equal to. At first glance, these inclusive inequalities might not seem very necessary. It is true that 2 is less than or equal to 5, right? But clearly 2 is not equal to 5, so isn't it more clear and just better to simply say that 2 is less than 5? Why are we adding some confusion here by saying 2 is less than or equal to 5? The answer to that question is that inclusive inequalities are useful in the context of trying to determine if some number is at least or at most some set standard. For example, if a person must be more than 48 inches tall to ride a roller coaster at Disneyland, then a 49-inch person can ride, but a 48-inch person cannot, because the person needs to be more than 48 inches tall. So if they're exactly 48 inches tall, that disqualifies them because they need to be more than that, right? In this scenario, if h is the height of a random person, then the requirement to ride the ride is that h is greater than 48. Their height has to be more than 48. But of course, that's not the way those kinds of rules usually work. Usually the rule is that the person must be at least 48 inches tall to ride, which means that if they're 49 inches, they can ride. But if they're 48 inches, they can also ride, because if they're 48 inches tall, then they are at least 48 inches tall, right? And so the requirement to ride the ride would no longer be h greater than 48. It would be h greater than or equal to 48, right? And that's why those inclusive inequalities are useful, okay? They're useful symbols for us. So with that in mind, let me just give you some examples, and then we'll be done with this review. Okay. Number 6 here says, suppose that a number x in a data set is considered an outlier if x is greater than 5. Determine if the following values are outliers. So the number is going to be an outlier if it's greater than 5, right? Well, 4.5 is not greater than 5, right? So this is not an outlier. Okay, what about 5? Well, a number is considered an outlier if it's greater than 5. 5 is not greater than 5, it's just equal to 5. So this would also not be an outlier. Okay, what about 5.5? Well, 5.5 is definitely greater than 5, right? Definitely greater than 5, so this one's an outlier. Okay, so this one was not greater than 5, right? That was a false statement. This one was not greater than 5. That was a false statement. In fact, maybe I'll put a slash through those to say, no, that doesn't hold. So those aren't outliers. But this one is an outlier. Okay? All right, number 7. So suppose that a number x in a data set is considered an outlier if x is greater than or equal to 5. Okay, now we're given the same numbers, 4.5, 5, and 5.5, and we're asked if they're outliers. But notice that this time, the criterion for being an outlier is different, right? 4.5 would still not be an outlier, because 4.5 is not greater than or equal to 5. But 5 would be an outlier in this case, because 5 is greater than or equal to 5. Okay, it's right on the cusp, right on the boundary. 5.5 would also, once again, be an outlier. Whoops. So we're going to see this kind of thinking a lot in section 1.4. So this kind of, these symbols and this kind of thinking will come in handy for us. Let me give you just one last example. It says, let u be, this is the Greek letter mu, and this is the Greek letter sigma. So u is mu minus 2 sigma. Okay? And suppose that an observation x is considered unusual if x is less than or equal to u. Part A asks us to calculate u if mu equals 5.8 and sigma equals 1.3. Okay, easy enough, right? U equals mu minus 2 sigma. We're told in this case that mu is 5.8 and that sigma is 1.3. So this would be 5.8 minus 2 times 1.3. So let's see in Desmos, 5.8 minus 2 times 1.3. Okay, so that comes out to 3.2. And then we're asked, is 3 unusual? Is 2 unusual? Is 3.2 unusual? Well, these numbers are unusual if they are less than or equal to u, right, which we just computed, right? So this is u. And if a number is less than or equal to that, then it's unusual. So, is 3 unusual? And the answer is yes, because 3 is less than or equal to 3.2. Is 2 unusual? Again, the answer would be yes, because 2 is less than or equal to 3.2. Is 3.2 unusual? Again, the answer would be yes, because 3.2 is less than or equal to 3.2. And just for good measure, I suppose, we could say, is 3.5 unusual? And the answer here would be no. No, because 3.5 is not less than or equal to 3.2, right? 3.5 is greater than 3.2. Okay, so that'll do it for this review.